Hello everyone. In the last class we discussed about geometric similarity, kinematic similarity and the dynamic similarity, and we saw that how certain non-dimensional numbers basically play an important role in governing the dynamics of the fluid flows. Okay. And particularly what we saw is that in typical flows where the medium is compressible, the Reynolds number and Mach number play a very important role, right. So, in today's class what we are going to do is we are going to non-dimensionalize the governing equations. We have already derived the governing equations, mass equation, mass conservation equation, momentum conservation equation, energy conservation equation. What we will do today is that we will cast all these equations in terms of non-dimensional numbers, right. So, your velocity, your length scale, your density, all these variables will be non-dimensional numbers, and we will retrieve some governing non-dimensional numbers from that. Okay. So, let us start the discussion today. Okay. So, before we start with the equations, let us see what are the scales with which we can non-dimensionalize the numbers, right. So, as we saw in the last class is that, for example, if you have a model and a prototype, you have to have the geometric similarity which gives you that what is the factor that they are related to, right. So, between a model and a prototype you may have a chord length, okay, this is C, this can be your 4 C, right. So, this chord length can be your reference scale to non-dimensionalize all the basically all the length scales, right, which can be x, y and z, right. So, we will call this reference scale as L. So, in the aerofoil it can be the chord length. Let us see if you are doing a cylinder, flow process cylinder, small cylinder and a big cylinder, right. So, this could be your D, okay. It can be a 4D or whatever D you have. So, the diameter of the cylinder can be your non-dimensional, I mean can be scaled to non-dimensionalize. Okay. Similarly, if you have a flow in a channel, the width of the channel can be one of the scale, right. So, you have to ensure that whatever length scale you are changing for the non-dimensionalization, your Reynolds number should be defined on the same length scale. Okay. So, what we are doing, we are non-dimensionalizing all these lengths. So, let us say this length is 4 C, and if you are non-dimensionalizing it by the chord length, your x star or basically L star becomes 1, right. Why? Because you are non-dimensionalizing with the same length. So, this is 4 C by your length which is L, so which is 4 C, that becomes 1, right. So, it does not matter whether it is model or prototype, you are non-dimensionalize everything by the chord length of the same thing. Okay. So, this is a reference scale. We need to non-dimensionalize with respect to your velocities also. Okay. So, this is u, v and w, okay. They are in meter per second, okay, not meter. So, we are going to non-dimensionalize with respect to some incoming velocity. Let us say on this wing there is a velocity coming in, okay, the total velocity basically u infinity. Okay. So, you can non-dimensionalize u v w by u infinity. So, that means your u star or let us say u hat will be u by u infinity, okay. And if let us say the angular attack is 0, then there is u v will be 0 and u will be 1, u will be u infinity, then it will become 1, right, and v hat will become v by u infinity, that will become 0, right. If there is an angle of attack, then it will be u cos theta, right, u hat will be u cos theta, basically u infinity cos theta by u infinity, that will become cos theta, and v hat will become u infinity cos sin theta by u infinity, that will become sin theta, right. So, if you have flow, let us say flow inside a channel or in a flat plate, then it is just u here, this is u infinity, right. So, then u hat will be 1, v hat will be 0, and similarly w hat will be 0, right. The third is your density. So, you can non-dimensionalize the density also based on the free stream quantity. So, that is rho infinity. Okay, this is just I am giving a reference scale. You need not use this same reference scale. You can use any reference scale that you like, right. But only thing that you need to make sure that whatever reference scale you are using, you should define your Reynolds number on the same scale, because you will see the importance of the Reynolds number when we derive the equations. Okay. If you define the Reynolds number on some other scale, we need to convert into these scales in order to use the derive non-dimensional equations, right. Similarly, the temperature can be non-dimensional with respect to T infinity. So, your T hat will become T by T infinity, which is 1, right. You can non-dimensionalize your viscosity based on the mu infinity. Okay. So, that will also become 1. So, mu hat will also become 1. So, I am representing all the hat quantities as the non-dimensional quantities. So, there is no unit of this. Okay. U hat, T hat, mu hat, they have no units. Okay. Now, you have the derived quantities also. So, since you have non-dimensionalized L also and U also, you can derive this time, okay, non-dimensionalized with respect to L by U infinity. What is the dimension of U infinity? Is meter per second, L is meter. So, if you do L by U infinity, that will be second. So, you can non-dimensionalize this, T equal to T hat will be T by L by U infinity. Okay. This is your T hat. Okay. Many times it is also represented in terms of the Struhal number. Okay. So, the Struhal number is a non-dimensionalizing quantity between the time and the time which is derived from the flow scale, the flow velocity. Okay. And lastly, you have the pressure. Okay. So, which is Newton per meter square. So, the pressure if you use P infinity, okay, you can also use P infinity, which is the pressure at the free stream. Okay. But you also have another quantity which has the same unit as the P infinity, which is the dynamical pressure, right. That is rho infinity U infinity square. It has the same unit as the pressure, right. So, if you use P infinity, you would see that you are basically getting a number which is basically P infinity by rho infinity U infinity square. Okay. So, rather than going into that, you can directly use this dynamical pressure, make use of that, and you can easily retrieve your non-dimensional equations. Okay. But there is no harm using the P infinity also. So, once you derive that, these are the hat quantities that I have written here, x I by L, u I by u infinity, rho by rho infinity, T by T infinity, mu by mu infinity, T infinity by L, and rho P by rho infinity square. Remember, this is a vector quantity u I. So, depending on the flow direction, okay, you will have u hat equal to let us say 1, v hat equal to 0, w hat equal to 0, or if you have angle of attack, then u hat will be let us say cos theta, okay, v hat will be sin theta, okay, depending on the direction, and w hat will be 0 or something like that. Okay. So, now that you have done that, let us look at the conservation equations one by one. Okay. So, we will start with the mass conservation equation. Okay. So, basically d rho by dt by del x. Okay. So, I have everything in the slides which will be given to you, but I prefer to derive it so that you can go through all the steps easily. Okay. So, here now I am trying to express all these rho, t, x, u, everything in terms of the non-dimensional quantity, right. So, rho hat was rho by rho infinity, right. So, the rho can be written as rho hat rho infinity, right. Similarly, t hat was t by L by infinity, which was t infinity by L. Okay. So, you can write t as t hat L by u infinity, right. Similarly, x I. So, x is now 3 direction x, y, z, but all are scaled by the same length scale, right. So, x I hat was x I by L. Okay. So, x I can be written as x I hat L, right, and similarly you have u I hat was u I by L. So, u I can be written as u I hat L. So, put all these things here, this is del rho hat rho infinity, okay, by del T hat L by u infinity, right, plus del by del x I. You can also write in expanded form, but it will, you can write del by del x rho u plus del by rho v and del by del z rho c. It will have the you will have the same result. Okay. So, this is del by del x I. So, x I is basically x I hat L, okay, multiply by rho hat rho infinity u I hat u infinity is equal to 0, right. Now, collect the terms together. So, we will have rho infinity u infinity by L, and this is here also rho infinity into L, and here also rho infinity into L, and then it will become del rho hat by del T hat plus del by del x I hat rho hat u I hat equal to 0, right. Now, of course, rho infinity u infinity by L cannot be 0. Okay. So, then you got your non-dimensional equations for the mass conservation, which is del rho by del T plus del by del x I hat rho hat u I hat 0, right. So, now you can compare your, this is your dimensional equation, okay, where everything has got a unit, rho is kg per meter cube, T is per in second, u is in meter per second, x is in L, and this is your non-dimensional equation. Right. So, here everything is unitless, but the both the equations look very similar, right. If you can just remove the hat here in this expression in non-dimensional equation, it will look like your dimensional equation, right. So, there is no change between the in the nature of the equation between the dimensional equation and non-dimensional equation, okay. But you will have changes when you go to the momentum and the energy conservation, right. So, this is what we have just derived, right. Now, let us go to the momentum conservation and the energy conservation. Okay. So, let us use the thing that you have done, del rho u I by del T plus del by del x j rho u I u j will be del by del x j tau I j and minus del p by del x I, right. I am ignoring the body force, but it will not basically change anything. Okay. Tau I j, okay, as you have derived for the Newtonian fluid. Okay. So, that was basically 2 mu E I j minus delta I j del u k by del x k, right, 2 by 3, right, 2 by 3 mu. Okay. So, we will use the same scaling that we had, except that for the pressure we are using, so p hat by was p by rho infinity u infinity square, right. So, you can write p will be p hat rho infinity u infinity square. Okay. The other thing we have is the tau I j. Okay. So, whether the flow is incompressible or incompressible, you can see that it is basically goes as mu into some kind of velocity gradient, del by del x or del by del y, whatever you want. E I j is basically depends on velocity gradient, and this is also velocity gradient, right. So, basically this is mu u by x, right. So, you can write it as mu hat mu infinity and into u hat u infinity, okay, by x hat into L, right. So, let us use those relation, okay. Or you can, I mean, you can be more precise, okay. You can use u I, use a and all those things, but it will come to the similar nature, right. So, let us start deriving here. So, this will become del rho hat rho infinity plus u I hat u infinity by del t, and what we have done for t was t hat L by u infinity, right, plus del by del x j rho hat rho infinity u I hat u infinity u j hat u infinity, okay. And what I will do here, I will just write del by del x j hat, this is L, and tau I j I will write tau I j hat, okay. And it will multiply with what? It will multiply with mu infinity u infinity by L, where I have defined this tau I j hat in terms of a non-dimensional variable. So, that is basically 2 mu hat E I j hat minus 2 by 3 mu hat delta I j del u k hat by del x k hat, right. So, if you do all those things, you will get this mu infinity u infinity by L, right, and minus del p. So, p is basically p hat rho infinity u infinity square by del x I hat into L, right. Start collecting the terms, okay. So, here you can see this is rho infinity u infinity square, and this is x by L, right. So, here also rho infinity infinity square by L, this is also rho infinity infinity square, because this is infinity here by L. The only thing, only difference here is this term, okay. So, we will collect all the rho infinity infinity square by L here, okay. So, this will become rho infinity u infinity square by L, and then you have del by del x t del by del t rho hat u I hat plus del by del x j hat, okay, rho hat u I hat u j hat, and plus I am bringing it on the left side, the pressure term, okay. So, then delta I j will come, delta I j you will have p hat, right, because I have taken rho infinity infinity square already on the left side, okay. This is on the left side, okay. Right side you have mu infinity u infinity by L square, right, del by del x j hat tau I j hat, right. So, this is your left side and this is your right side. If you take all these left term on the right side, so what we will have is del by del t rho hat u I hat plus del by del x j rho hat u I hat u j hat plus delta I j p hat would be equal to mu infinity u infinity by L square multiply by, I am taking all this thing on the right side, L square by rho infinity u infinity square is L, okay, not L square into del x by del x j hat tau I j hat, okay. If you can manipulate this number, okay, L will cancel out, u infinity will cancel out with 1 infinity. So, what number you have here is mu infinity by rho infinity u infinity at, right. So, what is this number? This is nothing but the Reynolds number defined based on your free stream density or whatever the density scaling that you have used for non-dimensionalization the velocity scale that I used for non-dimensionalization, the length scale used for non-dimensionalization, and your the viscosity scale you are used for non-dimensionalization. So, if you can define your Reynolds number based on those scales, you can cast your entire equation in terms of the Reynolds number is the governing parameter, right. So, your equation will look like del by del T hat rho hat u I hat plus del by del x j rho hat u I hat u j hat, okay, 1 by r e tau by tau del by del x j tau I j hat minus del p hat by del x I hat, right. Now, compare this is the dimensional equation and this is your non-dimensional equation A and B. So, if you compare, okay, the only difference in terms of nature equation that you will see is that you have this 1 by R e term appearing in your viscous stress term, okay, and that is a very important term. Okay. So, whenever you are trying to solve, let us say when you use a non-dimensional solver and you fix your R e, okay, because all your numbers are non-dimensional numbers, right. Your how does the initial force contributes in the flow will be dictated by this 1 by R e number, right. So, that is what this equation says, right. So, remember all other numbers that you see are basically the non-dimensional numbers. So, this is how we have derived the momentum conservation equation. If you want to write your in the tau I j hat in your long form, you can write it like this. Okay. Now, let us look at the energy equation, which is the most sophisticated expression here. Okay. So, let me just do it, del by del T rho E plus del by del x j rho, either you can write rho u h or you can write rho u E plus P, okay, plus rho P, P u, right, I think, yeah, rho u j h. Okay. So, E plus P by rho gives you the enthalpy. I am writing it in a separate form, so that it will be easy to for you to grasp, and then you have del by del x j u j tau I j and plus you have del by del x j u j, right. I hope I am right. Yeah. Okay. So, this is your total energy equation. Okay. I am not deriving the thermal energy equation, this is the total energy equation, or we are going to non-dimensionalize that. Okay. And when you use the Fourier's law, the q j becomes k del T by del x j, right, that is the Fourier's law. So, where k is the thermal conductivity. Okay. So, here I am defining internal energy as E plus P, E plus K. So, rho E is equal to rho E plus rho K, okay. So, rho E, which you can express in terms of CVT, and plus rho u I by 2, right. So, if you want to express in terms of non-dimensional terms, so u I is basically you can written as u by u infinity, right, your hat is u I by u infinity, right. So, here this entire term rho E can be written as rho hat E hat and multiply by rho infinity u infinity square, right, because u I E hat is u I by u infinity, but you have u I 2 times coming, right, and you can express this also in the similar term, okay, rho C B T, which will become rho R T, that will become P. So, let me make it clear. So, rho E will be rho E plus rho u I by 2, and rho is basically rho C V T by CVT, right, plus rho ui by 2, and CVT is nothing but rho RT, R by gamma minus 1. So, rho RT by gamma minus 1 plus rho ui by 2, and the last term this becomes rho RT is P by gamma minus 1, right, and rho ui by 2. So, P we have taken the same scale as rho infinity u infinity square, right. So, you can choose this T square for the entire term, right. Remember the first term is expressed in terms of P, second term expressed in terms of rho u square, right. So, this entire term can be scaled in terms of rho infinity u infinity square, right. So, then let us write this. So, this is del by del T hat and del T hat, and then it will be L by u infinity, right, and this is rho hat E hat into rho infinity u infinity square. Okay. Similar thing come here also, del x j hat into L, this is rho hat E hat rho infinity u infinity square multiply by u j hat u infinity, right, and plus if you take the pressure term, it will also have the same thing, del by del x j hat L in terms multiply by P into rho hat u hat square infinity square rho infinity square multiply by u j u infinity square, right. If you go to the next term, del by del x j hat into L, and tau I j we have already discussed, right. So, tau I j goes as tau I j hat multiply by rho mu infinity u infinity by L. So, that will be u j hat u infinity into mu infinity u infinity by L into tau I j hat. Okay. Now, this is a very critical term. Okay. This is minus k. Okay. So, I will write it in terms of your this variable in terms of temperature, I will express it using the Fourier's law. So, this will become k del square T, right. Okay. So, this will become k del square T. So, this will have the similar terms. So, right now it is become rho infinity u infinity q by L, and all these LHS term will be present there. Okay, del by del T rho hat E hat, okay, plus del by del x j hat rho hat u j hat E hat plus P hat u j hat, okay, is equal to here what are the terms that you are getting, mu infinity u infinity by L. So, this is mu infinity is on the left side, mu infinity u infinity square by L square, okay, and del by del x j hat u j hat tau I j hat. Okay. The only thing that is remaining and that we have not done anything so far is basically your this thermal conductivity term. Okay. So, before working on that, I need to introduce another number which is called the Prandtl number. Okay. So, what is Prandtl number? This is mu Cp by k, okay, or you can write it as mu by rho by k by rho Cp, okay, which is nothing but nu by alpha. So, you know all both these terms, nu is basically your kinematic viscosity and alpha is your thermal diffusivity. So, the Prandtl number is a ratio of the momentum diffusivity to the thermal diffusivity. Okay. The kinematic viscosity is also called the momentum diffusivity. By thermal diffusivity. So, this number is very important. Let us say you have a solid surface, okay, and the solid surface has got certain conductivity and there is a flow happening on top of that, right. So, the heat transfer will take place. Okay. So, there will be diffusion due to the momentum and the diffusion due to the presence of the conductivity, right. So, the Prandtl number defines the ratio between the two, right. So, if we write it in terms of your mu Cp by k, right. So, you know the variation of mu, right. So, the because we have non-dimensionalized mu in terms of mu infinity. So, we can write this k in terms of Prandtl number into Prandtl number by mu Cp, right. So, k will become because mu Cp by k is equal to Prandtl number. So, k will become PAR by mu Cp, right. So, I will write this term plus Prandtl number by mu Cp into del square T by del T square, okay, or just write del square T, right. Now, T is expressed in terms of T infinity, right, and mu is expressed in terms of mu infinity, right. So, if you use those, okay, now let us start arranging all the terms. Rho hat E hat plus del by del x j. I am keeping all the left hand terms in the form which is very close to the dimensional form P hat U j hat, and the right hand side if you see. So, you have this L. So, L will cancel out with this L square, okay, and this U infinity will go down. So, it will come to the same expression as 1 by R e, okay, like we did for the momentum equation, right, rho u L by mu. Okay. So, this u q will go down here, it will cancel out with u square, this will become u infinity, and so let me just write it before you go there. Rho infinity u infinity L by mu, right, del by del x j u j hat tau I j hat, right, and plus you have this L by rho infinity u infinity cube, right, because you are putting all these terms on the right hand side, okay, multiply by P r by mu into mu hat into mu infinity. Okay. Remember, P r is already a non-dimensional number. So, we do not have to basically further non-dimensionalize it, okay, into C p and multiply by del square T hat into T infinity, and because we are also non-dimensionalized del square which is del by del x square, right. So, this is del 2 by del x j square. So, then there will be L square here as well, right, because remember this is del square by del x j square, okay. So, that is basically del square by del x j hat into L square, right. So, that is the L square that I have written here. So, now we have to finally just rearrange these terms and we are done. Okay. So, I will just take you here. Okay. So, I have written that term as term A, okay, and all those terms, this is mu hat, T hat and everything are present there. Okay. So, this term is now A. Okay. So, we have taken this L by rho infinity cube here, okay, and then you have this mu infinity T infinity term coming from here, okay, then C p is there, and then you will have L square, and then there is a Prandtl number, right. So, what you can do, you can express these terms into 3 different non-dimensional numbers. Okay. So, because there is a presence of mu infinity, you can basically first sort out the Reynolds number. So, this is mu infinity by rho infinity u infinity L, right, and so you got this rho infinity u infinity L from here. So, anyway L square will cancel out. Now, you have u square present, right, u infinity square present, right. So, this is u infinity square, and then what we will do, we will we have temperature here, I will write gamma r T infinity. Why I am writing gamma r T infinity? Because we can sort out the Mach number. This is A square, this is u square, right. and then remember Cp is gamma r by gamma minus 1, right. So, we have used this Cp is gamma r by gamma minus 1. So, that will gives us the gamma r T infinity, okay. And then finally, what is left is 1 by gamma minus 1 into Prandtl number. Okay. So, this is your Reynolds number. So, this is 1 by Re, this is 1 by Mach number, and Mach number is square, and this is 1 by Prandtl number into gamma minus 1. You can see the thermal conductivity term has got so many terms. So, finally, 1 by Re, Pr, Mach infinity square, gamma minus 1. Okay. So, when you use a compressible solver, you put a Mach number, and that is where the Mach number comes in your non-dimensional equation. That is why this Mach number does not appear in your momentum and your mass conservation equation, right, because when the flow is compressible, you do not need an energy equation, right. So, you do not need a Mach number there, but for a compressible flow your Mach number comes here in the thermal conductivity term, right. So, you can finally express your energy conservation equation in the non-dimensional form in this form, okay, rho E by del T, this form, and I have used this sigma I j, but this is basically tau I j hat. Okay, it has got the both the terms of hydrostatic stress and the no, you can actually write in sigma I j only, because I have used H here, okay, which is the enthalpy. So, the pressure term is pressure stress is absorbed here. Okay. So, you can write it in terms of sigma I j. Okay. Remember tau I j is equal to minus P delta I j plus tau I j deviatoric. Okay. So, the tau I j deviatoric is written in terms of sigma I j here. Okay. So, the 1 by Re terms appear here, and finally, you have this 1 by Re Pr Mach infinity square gamma minus 1, which is appearing in your the thermal conductivity term, and here you do not need a thermal conductivity, okay, but you can just use the use your viscosity, non-dimensional viscosity, and that will work, and it works for the most cases, because see the Prandtl number, the variation in Prandtl number is very small. Okay. So, your thermal conductivity may change with temperature, your viscosity may change with temperature, but the ratio between the two, which is nu by alpha, basically does not vary too much with the temperature. Okay. So, you can safely use the Prandtl number to be I mean typically for the air it is used around 0.7 or 0.71. Okay. Although there are studies with the variation in the Prandtl number, okay, but for the normal cases at normal temperature variation, which is not very high, okay, in those cases you can assume the Prandtl number to be constant. Okay. So, finally, the last I mean missing piece in the cube that I want to talk about is the equation of state. So, where P equal to rho R T. So, this you will use for the dimensional equation. For the non-dimensional equation you have to change that also, where that is also basically very important. So, you can write P hat rho infinity square, rho becomes rho hat rho infinity, R is R, and T as T at T infinity. Okay. So, then P hat becomes rho T by gamma, and this is gamma R T infinity by infinity square. You can express it in terms of Mach number. So, the P hat becomes rho hat T hat by gamma m infinity square. Okay. So, this is your equation of state in terms of non-dimensional quantities. Okay. So, the finally, you can write if you can remove all the hat for the convenience. Okay. So, this is your non-dimensional equation for the compressible flows. Okay. So, you can see the first one looks very similar dimensional form, the second one is also very similar, except that you have this 1 by Re term, okay, and the third one has got this 1 by Re term in your stress term, and 1 by Re Mach square gamma minus 1 in your thermal conductivity term, and your equation of state I mean changes, and it becomes P equal to rho T by gamma m square. So, if you are developing a solver for the non-dimensional flow, you will be basically solving these equations. If you are developing a solver for the dimensional flow, you will basically ignore this 1 by Re and all these terms, okay, and you can write your solver accordingly, and there P will be equal to P equal to rho R T. Okay. So, with that we will stop here. In the next class we will start looking at the basically different PDEs, because you can see these equations, they have got all kind of they have got advection term, they have got diffusion term, and all these terms have got different behavior, and the way to solve them numerically are very different, right. So, we will look at the nature of different PDEs and we will characterize them in the next class. Thank you very much.